Hello, I'm Jaime from Nonica.io. I work as a director at Nonica. Today I'm going to talk about integrating AI into Revit. So yeah, let's jump in the presentation. So just a small disclaimer before actually starting the presentation. I'm not an AI expert, and yeah, I don't claim to be. What I'm presenting today, it is the results of my of my research and development process, my honest thoughts. So I'm trying to share here my lesson learned. Just a little bit of context about the presentation. This presentation is mainly focused on AI cloud-based renderer for Revit. So the solution was implemented as a C# Revit add-in after 6 months of work of research work. There was a 3-month beta release. I'm going to talk about the beta release closer to the end in this presentation. And after that, the project was discontinued. So it is not for sale. And the reason why this project was discontinued was mainly because this was a highly demanding project and requiring often updates and work on it. And we're a small company and had to put it in a standby to focus on on our main line of work. So the goal of this presentation is to open up that development process, to share workflows, opportunities, and the potential of these AI technologies, my lesson learned. But also, and more importantly, to share the obstacles, the limitations, and the failures along the way. So the goal of this project was to fully integrate AI rendering into Revit. At the time, Evolve Lab had recently introduced betas. I was impressed. I was impressed by betas, and I was eager to try what was possible to explore the possibilities of AI rendering into Revit. The result was then able to generate these realistic images directly from Revit, considering descriptions from the user about the desired image. So everything was encapsulated and run within Revit. So initially, I'm going to go to the very beginning, to the thought process. I found two separate systems. On one hand, I had the Revit model. On the other hand, I had the AI model. Well, each system has his own way of managing geometry and data and so on. So then the question was, well, how can those two systems be brought together? Yeah, I initially focused on the intersection between both. I felt like, okay, what does actually AI need from Revit? For me, it was a little bit easier to think that way because I already had some experience programming in Revit. So it was easier to try to think to adjust Revit to what the AI actually needs. So that can be actually broken down into three things. The first thing is the prompt. The second is the image. And the third thing is the parameters. So I'm going to skip the prompt part in this presentation. Well, I think it's already well documented in other presentations and online resources for time constraints as well. And I want to focus mainly on the image part and the parameters part. So the image part, this is one of the most important part for the AI, for the inputs of the AI. Well, image-to-image models, AI models, require an initial image to generate accurately images. So luckily, Revit API provides some built-in methods that helps exporting what the user is actually seeing. So they export like a screenshot of what is being shown to the user. And that was great. That was the first step to get what the user was seeing, to gather all that information and to use that as an input. And as a second step, a more conceptual image was required. The goal of this second image was to have a higher degree of control over the image generation for the AI mainly. This was for ControlNet. This more conceptual image was used for ControlNet, and ControlNet is it's a concept that I'm gonna explain in the next few slides. So I will go back to this in a few slides. But before, Revit has a visual engine that it can be used to and changed to extract those images with different styles. So I changed this visual engine to actually extract the image, the hidden styles, image type of Revit style that I needed. So I chose that specific visual style, like hidden lines with white background and with no shadows, mainly because of two reasons. So the two things behind this choice was, the first one was the textures and materials. There are certain styles like texture or realistic visual style that process and render texture in a way that when that image is processed for the AI, those textures and material can be pre-processed as noise. What I mean to put it into an image is, for example, in this image over here, we have the ground floor with a purple tile. That was translated in the image used for the AI that we see at the bottom. That was translated into a lot of different lines. So that's mainly noise that was causing the AI to not understand what was going on there, or mislead, generating different objects or ignoring, for example, the furniture in this case. So that was one of the reasons why hidden line style was chosen. Another reason why it was chosen was, also because of the shadows. I chose not to use shadows because when I tried to use them, those were translated into edges or lines. And also in the image, we can see that, for example, the main volume here has some drop-down shadow that goes over the floor and the wall. That led as well the AI to think that, that line that is in the bottom that we see, that led the AI to think that that was a change in the volume or a change in the texture. So it was as well misleading the AI for the generations. So that was mainly the two issues that I found when creating that conceptual image. So I needed to get rid of all those corner cases, and that's what I chose mainly. Hidden line style with no shadows for the conceptual image. So great. So ControlNet. What is ControlNet? This is one of the most important part for controlling the outputs of the AI. ControlNet is mainly an extension for specific AI models. It started for Stable Diffusion 1.5, and it provides a higher degree of control over the image generation. So yeah, I want to give credit to Ilias Viel, who was the developer who put this out there. It is great, the control and the power it brings over image generation for the AI. There are different type of control nets. Some of them are included here. There are others that are not included here. But mainly the concept is that it allows to define the structure of the image that is going to define the structure of the final image. It's like defining the skeleton of that final image. And we see here, for example, we have like different examples. That skeleton is going to be used for different variations. So each different type can be combined with others. They can be applied in combination, applying different weights, or they can just be applied in isolation. So that's what I went for. I applied one of them in isolation. So I applied Canny. I found that this is one of the well-documented ControlNet types. There's a lot of online resources, NuGet packages as well, and it is also quite popular in image pre-processing. So image processing is, of course, a very wide topic. I'm really I don't have a lot of experience in that sense. I barely touched a few concepts that I explained in this presentation. But the thing is like the image at the top is like the conceptual image that we previously extracted. And then I needed to produce an image that looked like something at the bottom, like the Canny image. So to produce that kind of image, my initial thought was like, if you ever use Photoshop or any other photo editing software, you may know about, well, inverting colors. So inverting colors works like, well, all the white color are going to be converted into black, and all the black colors are going to be converted into white. So my initial thought was like, okay, what if we just invert the color? So I got something like this. And that wasn't really a good idea. So I try other type of ControlNet with these images. Well, I tried with MLSSD, with head types as well, but any of them was actually producing good results in a range of images. The main reason, the main issue that I found with this type of images was that was the line thicknesses. The line thicknesses were appear quite natural for our eye, for the human eye, but actually the AI were not well ready to interpret them. So they were misleading the AI in some sense. But also, like in this translation, some thin lines, like for example, the floor texture, or well, the front wall that we see at the end of the room, that we have some vertical lines. Those lines were really thin. The AI literally just ignored them. So in some cases, like walls and well, certain surfaces that has materials ended up being ignored or interpreted in a different way. So what I actually needed was something like this. I needed the actual edges of the conceptual image. To get to that, I found that there were some NuGet packages to extract and to process to Canny. Those two packages that I know that I found was EmguCV and OpenCV Sharp. Those two packages were really helpful in that conversion. They were actually not that complicated to use. So I leave the code as well here in this slide. Yeah, actually the conversion was done in one line. There's a few parameters like the aperture, some threshold as well, but once you try a few times, you get usually good result quite fast. It is worth saying that including this type of packages can increase the size of application by a few hundred megabytes. So if you decide to use them, just be aware that your app for the deployment is going to be a little bit heavy. But there was a bigger problem. There was one problem with these two libraries. There was one limitation. And the limitation was that they rely on something called the Windows Media Feature Pack. And the Windows Media Feature Pack is included in Windows operating system, in Windows installations, by default in most installation. But there is one exception. And that exception was the Windows M version. And the Windows M version was released by Microsoft after the EU dictated that they were following monopolism practices. Therefore, Microsoft was forced to release this Windows M version. And the Windows M version is pretty much the same as the standard version, with the only difference that they don't include the Windows Media Feature Pack, well, the Windows Media Player, some image and video codecs. So therefore, I started to, well, trying to run these two libraries, the EmguCV or the OpenCV Sharp, will lead to exceptions or errors in the execution of the execution of the code. So I started to explore ways to solve this issue, this limitation. Of course, you don't want a range of users to find errors in your application. So my initial thought was like, okay, let's try to deploy this package when necessary in my app. But of course, the Windows Media Feature Pack is copyrighted by Microsoft, and it cannot be redistributed with third-party installers or application. So that wasn't really a solution. So I ended up, finding a workaround and ended up checking system requirements at installation time. So for installers, I use Advanced Installer, which helps me create MSI and exe files. Well, this solution for creating installers and also others, I believe, also provide this feature, allows to check for specific components or, well, system requirements at installation time. So I could check if the user actually had the Windows Feature Pack installed when they were installing the app. If they didn't have the pack installed, I could notify them and well, provide a link to go to the Microsoft web page to install. Of course, it's not ideal for the user to have to go to an external link to install an additional package, but that was necessary for those cases, and had to work it out that way. Great. So I was here. I was in the intersection between the two systems. So I cover mainly the image part so far. So let me update this. We got the image processing in between the Revit model and the AI. And now I want to focus on the parameters part. Well, for the AI to output images in the generation, there are quite a few parameters for the request. So, and not all of them are included here. I try to make like a selection of the most important, but in this session, I'm gonna focus mainly on 3 concepts. So there are 3 concepts that help me quite a lot for 3 different purposes. So the first concept is the base 64 images. Well, the images previously extracted in the previous section, the conceptual image and the initial image, those needed to be provided to the AI. So there are different ways to provide those images to the AI. Well, the faster and more convenient way that I found was using base 64 encoding. Base 64 encoding enables to convert an image into a really long text, a really long string that can be straight away injected into the request. So the AI can straight away, when the AI receives the well, the request, can straight away start processing the image. It's already there, the resource. Well, for example, the image could also be provided using a URL link, but to be honest, I don't think that's a good idea. I think it's better to use base 64 because if you provide a link, the AI has to, well, access that external resource, download the images, and then, well, after that, start processing. That can cause delays because maybe the URL, the server that has the URL link, well, is delayed for some reason at some point or is down. So that can also, yeah, affect the user speed. So I really recommend to use base 64 images. The second concept is related to 2 parameters. It's related to the denoising strength and to the classifier free guidance scale. Those two parameters define how close the final image is going to be to the initial image in regard to the prompt. I label them as material creativity. So basically, the higher those 2 parameters are, the more contrasted and the more vivid the final image is going to be. So to put it into visuals, at the top we have like an initial image that was used for the rendering, and at the bottom we have a low material creativity image. So we see that the AI interpreted some trees, some vegetation around, but still like the material of the house remains pretty similar to the house. So it remains white and pretty similar in that sense. In contrast, a high material creativity will look like something like this. So we see now like the trees are also more contrasted, the lights as well of the scene are more contrasted, but the materials of the main house are also well, more vivid and more different than the previous image. So that will be a high material creativity. So this and the next concept will also help the user to adjust to their needs when rendering. The next concept is geometry creativity. And this is linked to, well, the ControlNet weight and to the ControlNet guidance strength. So this is going to define how strong is the structure of the image, the skeleton that we previously defined for the final rendering. So the higher the value, the more creative the AI is going to get, changing the structure of the image and producing different images with different structure. So to put it into visuals again, we have an initial image at the top, and we have a low geometry creativity image at the bottom. So in this case, mostly, of course, there are some changes like following the prompt, like materials and so on, but it's still like the main structure of the image, how the furniture is located, the dimension of the space and so on is pretty much the same as the initial image. So that will be a low geometry creativity image. And this one will be a high geometry creativity image. So there are bigger changes here. We see that the furniture has changed a little bit. There's still some patterns follow from the initial image, like for example, the sofa in the left. We see that there is some kind of like sofa as well there. But mainly, there are some bigger changes also in the space and the furniture arrangement. So that's also another parameter that was used by the user depending on how big difference they wanted to have from the initial image. So those three concepts were key for the parameters. Great. Going back to the process diagram. Most of the previous slides and the efforts in this presentation has been so far focused on controlling the AI and the inputs of the AI. But remember that we're still in the intersection between the two systems. And that means that we can still have control over the Revit model. So that opens a new range of possibilities using Revit API before actually pre-process the image. Likely Revit sorts element by category. So we could, for example, hide any of the categories to reduce the constraints for the AI. And what I mean, for instance, is if we want to generate different furniture proposals in the image shown, we could, with the Revit API, hide the furniture category, then export that image using the Revit API as well, and then undo the transaction to maintain the view and the model unchanged to the user. So we'll get an image something like this. And that will help to reduce those constraints so the AI can freely start from scratch in that sense and produce the new furniture to something like this or to maybe something like this. So a similar technique could be used to generate variations of facade design, for example. So we could hide, for example, the windows or the doors category, and that will again reduce the constraints for the AI to produce new designs and new variations of the main volumes. So going back to the process again. Now we got all the Revit model and image processing part covered, and now I want to focus more and cover more the pure side of the AI. So I want to focus now on the model. At the time, Stable Diffusion 1.5 was the only AI model that had the ControlNet extension, that have that higher degree of control over the generation. But the downside was that the 1.5 model had a maximum resolution of 1024 by 1024. And of course, that was not enough for high quality architectural renderings. So especially some architects need a higher resolution for that than that. There was an alternative model, the XL model, which did not have the ControlNet extension. But as well, to be honest, I didn't like the idea of having two models deployed for the two different resolutions, as that will increase the corner cases and increase the complexity of the application. So what I found is that many API services provide something called upscaling. And this is really nice because the image, the Stable Diffusion 1.5 model can be used to generate an image of 1024 by 1024 pixels. And then after that image is generated, there can be a second step that is called the upscaling. And the upscaling makes the AI increase the resolution of the image using the upscaling factor. So if I use a factor of 2, the AI will increase the resolution of the image to 2048 by 2048 pixels. The cool thing is like this two-step generation can be done in one single HTTP call. And that's great because I didn't have to make the first generation, get the images, and then send another request. But instead, the deploy model could straight away do the 2 steps and then give me back the high quality images. Of course, as you can imagine, the higher the upscaling factor, the longer it's going to take to generate those images. But regarding the AI models, there are hundreds of different variations of Stable Diffusion 1.5. They are fine-tuned by users and the community. There are websites like Hugging Face or Revit AI that you can access, download those models. So I started trying many of them. So I wanted to find a model that work well for this purpose. So I found that one of them called Realistic Vision 5.1. I think there is already newer versions of this one, but this one specifically was the one that I deployed. Brought actually good results in my experience. So this model was fine-tuned for hyperrealism and photorealism, and therefore it was generating highly detailed images of interior design and exterior images. But I found one limitation with Realistic Vision 5.1, but also with other AI models that I try and work with. And the limitation was that when I tried to render floor plans and section views, those were not really interpreted well by the AI. And in some cases, some part of the view was understood as a 3D view, or even the view of the furniture was not really rendered well by the AI. So I went into training. I thought, okay, let's explore these options and see what is possible with training. Maybe there is a solution there. So I tried to decompose the different layers of AI training into this slide. So generally, the closer we are to the neural network, the more influence we have on the final results. So, but that also implies that there is a high risk for misconfiguring the model and, not really making it work. So starting from the top, the LoRA layer is like the final filter to the output of the AI model. LoRAs are external. They can be used to specify that an image looks like, for example, like a watercolor or like a hand drawing. So they can be used for this type of filtering. One of the good things about LoRA is that they can be specified at request time. So we can have like a main model and then have like different LoRAs. And whenever we make a call, we specify the model we want to use, but also which LoRA. So that's pretty handy if you have like different user case that can help you produce different results. For example, as I said, with different styles of images and so on. So LoRAs can usually be trained in online API services. So if you deploy your model that way, you have the option to upload your data set, your set of images, and train the LoRA there, and then access straight away from there. But to be honest, I recommend to do it with Python. There is higher possibilities with that. You have more parameters, and you can customize further how the LoRA is trained. So the second layer is fine-tuning. So, for the study case, I mainly try to, to train a LoRA. But to be honest, training a LoRA for the floor plans and section views were not really productive for that use case. So I gathered all the images and I trained the LoRA, but it wasn't really producing good results. Nonetheless, I try also with producing images of industrial buildings. So I train a LoRA for that. And in that case, it seemed to work well. So that's something that, I think training a LoRA can also depend on the use case and also the images included in the fine-tuning and training of the model. So going back to the fine-tuning, this is of course more resource intensive. So the number of images start to scale up. To fine-tune a model, I wouldn't recommend to do that locally in a computer. That can take days, weeks even. So that can end up burning up a laptop or a local computer. So I think it's best to just do that if you want to do that, like of course, in an Amazon Web Service or something like that online. So, and finally, we have the training, which in this case was done with Stability AI, which requires, millions or billions of images. They have like this huge data set of images and also requires a significant investment. So for the study case, the floor plan and section limitation was something that I didn't actually end up finding a solution for. I also saw that, most of the models that I try and solutions as well were limited in that sense. So the renderer will be limited as well in that sense. That's something to research further. So now we have the model. I had to find ways to actually deploy to share it to other users. There are benefits and drawbacks linked to the number of users and requirements. So depending on the situation, the type of deployment may make sense, or another one may make sense. The first one is local models. They are usually not feasible options for teams. If it is 1 or 2 users, maybe makes sense, but AI models are quite heavy. They can be like tens of gigabytes, and it can be challenging to update and handle operations if deploy locally. So the second option is cloud infrastructure. So this alternative includes renting the infrastructure and deploying the model yourself. There are like built-in options like that have like click and go options like run pods. So in a few clicks, you deploy a Stable Diffusion or other models in the cloud, and you can just start calling from there. So this option I think is the best for a large team, and it offers a high-level customization. For those cases, I think that's the way to go. It has also the best performance. There is no shared queues, so the resources are dedicated for you. And also, you have the possibility to, for example, customize how concurrent requests are managed. If you want to, have a queue that waits the renderings, if you want to open new lines of resources and, process faster. So that also something that can be customized. So the price this type of services is usually paid per hour or per minutes of usage. Well-established brands and good brands, I think, are like Rampot or Hugging Face. So the third option is Cloud API. This is the option that I ended up working with. It's pretty convenient for initial testing, but also for small teams. It is fast to start with. There's no need to set up infrastructure. The downside is that they usually have like shared queues, meaning that if there's other clients in the same server than you, if their demand increases, your loading times and your response time will also increase. So that can affect the experience of your application. That can increase the rendering time. So it is good to say that there are many online APIs providers that overpromise but end up not delivering. So it is good to make good choices in this sense. or it can become a nightmare. And the price is usually per API request. Yeah, I would recommend well, Replicate.ai or GetImage.ai, as those are, I think, well-established brands and offer overall a good experience. So going back to the process again, diving into the final image, how to present that to the user. So generation can include as well webhooks, which is basically like a URL link that receives a notification when the render is finished. So this is quite common in platforms like Zapier.com or Make.com. And sending information to a webhook from a C# Revit add-in is, of course, very, well, it's kind of like straightforward. It's sending a request with the information you want, but receiving and generating that URL link at runtime to receive a notification is a different thing, and especially within the C# environment, well, within the C# Revit add-in environment. So it became a challenge. Most of the documentation and resources are based on ASP.NET projects. So I ended up working with estimated times. So basically, when the request was initially made, the server will provide like a response with the well, the base queue, the estimated processing time based on the queue that was at that time and the available resource. So after that time was completed, the Revit add-in was then accessing the images, downloaded them, and presenting to the user. So for post-processing, there were a few actions enabled to users, like cropping, saving, or re-rendering. For that, I just use a system drawing image, and there were some methods and classes there that were used straight away. So I thought the diagram was completed. But an extra step came out when I was planning the beta release. I think in most the purpose of a beta is to actually improve the tool. I started to think how to improve the renderer during the beta release. For that, well, in the beta release lasted for 3 months. There were 30 users engaged. Average time was 31 seconds rendering time, and there was 1,605 images rendered. So the goal of the beta release was to to collect as much information as possible about how the tool was responding and how the user experience was. So those two things were key. Apart from gathering recurrent feedback from the beta users, like in meetings and emails as well, also anonymous usage data was collected. So in order to do that, I had to follow GDPR guidelines. So user had to explicitly agree and allow us to collect the anonymous data, but also, well, it was required to transfer and to store that information securely. So that information had to be encrypted. And for that, I use, well, RSA asymmetric encryption, which is something, an algorithm that is used in the banking industry and the digital signatures use as well. So that is actually quite secure. Yeah, I then wanted to also explain like the fields of data that were gathered and why that information was gathered. So the first one was date and time. So date and time was gathered to find out concurrent requests to the server, to find out mainly the performance of the server, if the server was going down or not, and how it was behaving. So then I had the rendering time to know about the user experience, if the loading time was within reasonable ranges, or if the user had to wait too long to get their images, of course. And finally, the status and errors to explore, well, potential errors that could be happening, not only the message and the information about the error, but also the line of code and all these kind of things that will help later on, well, fix those errors and take it to production. As the AI was deployed using online API services, a provider, collecting that data server side was not really an option. So I didn't have access to the server in that way, so I couldn't do it. So instead, what I ended up doing to collect that data was to set up a webhook using PHP So all the apps, all the client sites will, whenever they finish their rendering, that data will be encrypted, and that data will be sent to the webhook online that will be like a central hub. All the data will be centralized in there. So the data could be verified and then stored securely. So whenever I needed to access the data, I will just download and access all the data encrypted, decrypted, and start working and analyzing it. So that was how data collection was enabled in the beta release. What is actually next? There is a lot of going on with AI right now that I haven't talked. For example, we have like MCPs, Model Context Protocol, RAGs, or new OpenAI agent-to-agent concept. So this is something that I haven't really started working with, so I cannot really give you a lot of feedback or well, details about yet. But something that I'm definitely gonna get into it, and that I do recommend you as well to check it out if you want to well, to get into AI as well, as I think these concepts are going to steer the industry in the next few years. So that's the end of the presentation. I hope it was helpful and that you learned something from my lesson learned. Thank you very much for your time. Yeah, how do you do? Thanks.